Welcome to the eighth week of the course. Last week we continued with our discussion on properties of entropy, mutual information, and KL divergence. In fact, the week before that, we had introduced these quantities formally and covered properties such as chain rule, concavity, convexity of these quantities, the data processing inequality. In the previous week, what we did was we covered more advanced properties such as Fano's inequality. We provided various variational formulae. In particular, we provided two variational formulae, one for KL divergence and one for mutual information. The KL divergence variational formula is the one which is closely related to this Gibbs variational principle, and the mutual information variational formula led to the information radius interpretation of the capacity formula. Then we proved Pinsker's inequality, and we also use we also use this variational formula for KL divergence to get Pinsker's inequality. Finally, we proved continuity of entropy, and we did this using maximal coupling lemma and Fano's inequality. So basically, in this unit 6 and unit 7, we cover different properties of these measures of information. These properties are very handy, and they can be useful in a lot of unexpected places. Then we move to Unit 8, which is mainly about information theoretic lower bounds, and we have covered two lectures on this unit. In the first lecture, we derived a lower bound for the compression problem that we had seen earlier in the course, and this lower bound was a single short bound. It was obtained using Fano's inequality, and using this lower bound, we were able to get a tight result for the asymptotic case when we are interested in characterizing the minimum number of bits required per symbol to store an IID sequence, an IID source, a memoryless source. And this result is known as Shannon's source coding theorem. It says that the minimum number of bits required per symbol, asymptotically, as the number of symbols goes to infinity and the probability of error goes to 0, is exactly the entropy of the common distribution, entropy of P. So we showed the Shannon source coding theorem. We also derived lower bound for Stein's lemma, which is the minimum, which is a result about the exponent of the probability of error of type 2, given that the probability of error of type 1 is less than or equal to epsilon, for the binary hypothesis testing problem. This is the Neyman-Pearson formulation. What Stein's lemma says is that this exponent for IID observations with common distributions P and Q. So you want to know if the sequence of symbols is generated IID from a distribution P or is it generated IID from a distribution Q. Stein's lemma says that the probability of error of type 2, the missed detection probability, for any given probability of error of type, so we haven't shown for any given part, but for vanishing probability of error of type 1, goes to 0 exponentially rapidly. So it goes to 0 so it basically is roughly 2 to the power minus n times some quantity, some non-negative quantity, and that exponent is exactly equal to the Kullback-Leibler divergence between P and Q. That's what Stein's lemma says. We already earlier in the course saw a scheme, basically the log likelihood ratio test, which gives you this exponential decay. And now what we derived in the previous lecture, the last lecture of the previous week, was a lower bound, a matching lower bound for Stein's lemma. Okay, so this is what we have been doing. We are at unit 8. By the way, if you haven't noticed, as of last week, we have kind of the structure of units and weeks have diverged. So I tried my best to keep it in sync, but it's unnecessary and it's just there's too much planning. So from now on, I'll basically just go on with my units, and I'll do this reviews every week so that you can catch up and try to anchor the course. But the basic structure for me in this course is this units, not the weeks. So I'll be uploading some of the partial units in the weeks. Okay, so we'll continue with the unit 8 on information theoretic lower bounds. And this week, what I'll do is three things. First, in this unit 8, I'll also cover a subsequent unit 9, at least partially this week. So in this unit 8, what remains to be done, and which we'll do this week, is we'll derive a lower bound for randomness generation. Then we'll derive a strong converse for Shannon source coding theorem. So this the converse result, the matching lower bound that we derived earlier, is sort of a weaker form of converse result. We'll derive a stronger form of this result, and such results are called strong converse results. I'll derive that. And finally, I'll derive present an approach to derive min-max lower bound for estimation problems. This is a very important tool. This is how Fano's inequality and information theory in general enters statistics, especially parametric estimation and non-parametric estimation. So I'll show you that general idea of deriving such lower bounds. This uses Fano's inequality in most cases. Okay, so this is the plan for this week. I hope you are enjoying the course. See you in the next lecture.